uh, final exam and some reminders as well. Okay, so the first thing is I want to make sure that if you guys can take that fall final exam survey, it's in the link that I sent you yesterday through Remind. It'll be quick. Most of you guys have done it already, but for those of you who haven't, if you can just click on that link through Remind that I sent yesterday, last night, and it's just asking whether you intend to take the fall exam or the fall final. You can change your mind if you want. Just send me a Remind message. But if I don't hear from you, I'm just going to assume that you're not going to take it. Okay. But I would say that about 2/3 of you have responded. So thanks for doing that. The fall exam is going to be 16 multiple choice, 90 minutes, open notes. If you're face-to-face, then you'll be taking it here. You can use your notes, bring your calculator, use your device, okay? But even though it's multiple choice, I'm gonna ask you to show your work. So if you just circle your answers without any work, then there's gonna be minimal credit there. So, however, that also means that if I see good work with what you've done, but that you show understanding of the concept, but you missed a problem, I may look to give you partial credit. So just to reiterate, this exam grade will not go in the grade book if you do poorly on it. So there's no negative impact from this final exam. But if it does help your grade, it'll go in as 15% of your semester grade, and it'll replace your lowest summative grade, either quiz or test, depending on which one is more beneficial to you. If you're a virtual student, then there's a penalty for late submission. So the exam is going to be released 5 minutes before and then be due 5 minutes after. So you have a 5-minute window on either side of 90 minutes. Got to get that in. Otherwise, if it's out of that time interval, then you're going to be losing points depending on how late it is. Okay, so try to minimize the potential risk of issues that you may experience as you take the exam. So, I think it's best to print out the exam. So if you have issues, if something, sometimes students, they take their exam on their device, and if it crashes, they lose all their work. So if you have it printed out, it's a lot. You can always take a photo of that work and send it to me through Remind, right? In fact, I think that's feels like the most reliable way. Sometimes email takes a long time. If Wi-Fi is down, you still have cell service where you can send that to me. And if you're taking it on the device, taking the exam on your device, maybe you want to download it or put it into a Word document on your device so that if it crashes, that it's just going to be, it's always continually saving. Okay, so take steps to mitigate your risk so you can avoid late submission. Okay, exam is curved, but the amount is still undetermined. We'll determine that later. Okay, any questions about procedure for the exam? Yeah.
Can it, if we do like somewhere in the middle, could it just replace the test group?
Right. So I'm going to look at the numbers and I'll only do what's beneficial to you. Okay. So maybe it's best to just replace your lowest quiz grade, but not put in as 15%. So I'll play with those numbers. Whichever combination gives you the best result, that's what I'll do. Good. Any other questions? So yesterday, I also sent you a link to the fall exam review page. So here, I'll just go through the schedule here. I have links for the fall semester summary sheet. So it's just a 2-page summary sheet, kind of highlighting all the concepts that we've done this semester. Derivative rules, if that's helpful, you can print that out. So today, I just want to focus on limits, continuity conditions. We haven't seen limits since all the way back in August, so I'm going to spend some time just kind of reviewing through that. Derivatives, related rates, derivative graphs. We haven't seen these in a while. I mean, we've seen related rates, but I think it's good to kind of go back and review some of those older type problems. And then curve sketching, EVT, mean value theorem. So I want to highlight some of those as we go through the topics as well. But what's available here are 3 kind of fall review packets. And I went through and I highlighted the problems that I think are best for you to practice with. So just kind of pick and chose the ones that I felt would be the most beneficial for you to practice with to prepare for this particular version of the exam. We still have a review day on Monday, so maybe I'll just kind of pick some problems or just do some miscellaneous problems, ones that we didn't get to this week. And then exam starts Tuesday, 7th period. But this is still going to be a full day. It's just that the second half of the day are all going to be kind of shortened. And I think, let me see, what's the order of these periods here? It's 3, 4, 5, 6, 2, 1. So after the 7th period exam, then we go through our school day, 3, 4, 5, 6, 2, 1, and they're all kind of slightly shortened. Yeah, they're all like 45 minutes, a little bit shorter. But we can also treat this like another review day. Okay. And then 1st and 3rd, 2nd and 4th, and then 6th and 5th. Because there's no, we made this exam into a no-risk scenario in the hopes that this will encourage you to take the final. And the reason why is just because, this kind of gives you a chance to kind of see things from a cumulative perspective, because ultimately we're working towards the AP exam, and the AP exam is going to be more cumulative than what we have now. So it's kind of like a way to kind of practice, seeing things from a bigger perspective of everything at once. Even if you do poorly on it, have that experience of seeing it from the perspective of a cumulative exam, and I think that will be beneficial for you next, heading into AP exam review, even if you don't do well on it. And also, it's not going to hurt your grade. So I encourage you guys to take it, even if you feel like grade-wise it may not help. All right, let me go through each of these topics, just kind of highlighting what to expect on the final exam. So limits, L'Hopital's rule, continuity conditions. We're going to focus on these today. L'Hopital's we didn't get to until chapter 2, but I'm going to show that there's a nice connection. We can do L'Hopital's rule with pretty much all the limit problems that we learned in chapter 1. Finding derivatives, finding tangent line equations. We've been doing that kind of continually through the semester, and we just saw it last quiz, which I started grading. They look really good, a lot of A's. So I'll try to get that finished and graded for you in the next day or two so you can see your results and see how it impacts your grade. So product rule, quotient rule, chain rule, implicit. Not only knowing how to do these, but then also knowing when to use them, right? Because you're not going to see a problem where it's going to tell you, hey, use product rule here. We need to be able to recognize these rules or a combination of these rules. Finding average rate of change. So average rate of change is just slope. So change in position over change in time. Or I may ask you to find average velocity. So to find average velocity, we don't touch velocity. We simply rely on position. We take our position order pairs and we do change in position over change in time, and that is how we find average velocity. Particle motion, being able to recognize the connection between position, velocity, and acceleration. They're just function, derivative, and second derivative. If I ask you intervals where the graph is moving left or moving right, we create a velocity sign line, right? We find velocity function. We set v of t equal to 0. We populate the velocity sign line, and then we test the intervals with the velocity function. If it's positive, we know it's moving right. If it's negative, we know it's moving left. Increasing and decreasing speed, we compare signs between velocity and acceleration. Increasing and decreasing velocity, we just look at acceleration. Piecewise, these are, number 7 is a very specific type of problem, so I'll go over that with you. This is a kind of a popular type of problem that they like to put on the exam, AP exam. Are these continuous and differentiable piecewise function? If you have a piecewise function and you have a bunch of constants that are that the problem is asking you to solve, what we can do is we can create some equations by the continuity portion means that these two piecewise functions, they must connect. And if they connect, that means they must share the same y value. If they share the same y value, we can set the two piecewise equations equal to each other. But then if they also tell us that these piecewise functions are differentiable, that means they're not only going to connect, they're going to connect in a way where it's a smooth transition. So that smooth transition, we can confirm by setting the two derivatives equal to each other and adapt to the fact that they must share the same slope at that point. And if we have the equations equal to each other and derivatives equal to each other, we have two equations that can help each other out to solve for the missing constant. Okay, so we'll hopefully get to some of these practice problems in the next coming days. Related rates, we just saw related rates with trig, but we're going to go through and practice the older related rates problems. Ones that involve volume and surface area of spheres, cones, and how cones require similar triangles. We'll review that. Okay, linear approximation. This sounds like a complicated concept, but really just focus on these two words, linear, right? Linear just means find a line, find the tangent line equation. So we know how to find tangent line equation, find the derivative, find the slope, find the ordered pair, point slope form. And then it's just one step beyond tangent line equation. Linear approximation, you're going to be given a decimal. You just plug that decimal into the tangent line equation. And whatever result you get, that's your linear approximation. Okay, we need to review our theorems, IVT, EVT, Rolle's mean value theorem. Most of these are coming from chapter 3. Okay. Interpreting derivative graphs. If you're looking at the f prime graph, we labeled, right, above the x-axis, below the x-axis. We used a slope or concavity sign line to kind of help bridge the information to get a picture of the original graph. We'll practice that as well. And then curve sketching topics, right? From f of x, we can find f prime. From f prime, we can populate our sign line. And then from the sign line, we can gather information about increase, decrease, relative max, relative min. From the second derivative sign line, we can gather information about point of inflection, if there's a change in concavity. Right, so all that we can practice through. And when we hit chapter 5, and the last trig unit, we began to see all these influx of new derivative rules, right? Up to that point, we're just working with power rule. But then, we had all these other methods within power rule, but we didn't see a lot of these new rules until chapter 5. So natural logs, or log base a, or exponential function e to the u, or exponential function a to the u. The trig derivatives that we just did last unit, arc trig derivatives that we just did. So being able to recognize when to use it and how to use it and how to apply those derivative rules. Also, log, if I ask you to find the derivative for log functions, we always want to do something first before we jump into the derivative, right? We always want to look to expand. So we learned about a couple of expansion rules, right? We learned about product property, quotient property, and the power property. And the idea is that we start off with a really messy looking log problem, but we can expand it out into multiple log problems. And even though that requires us to have to do separate log problems, each of them are a lot easier than having to do one messy log problem where you got to do a combination of product, chain, and quotient. So if you see a messy log problem, we always want to look to expand first. Okay. Log differentiation. This is where we look at a problem and we realize that we don't have a rule that can handle our scenario. A variable expression raised to a variable. Okay. And because we don't have a rule that can handle this, we use log differentiation to force it into a different form. And the idea here is we take the natural log of both sides, which will then unlock our power property, which we can bring down in front, and we can rely on product rule to find the derivative, implicit on the left, and then solve for dy dx. Okay, so we saw this in chapter 5, most recently. And finally, find the derivative of inverse at a point. All right, this is where the concept that we have, I like to go through this chart here. If I'm trying to find the derivative of inverse at b, I know that the inverse is that the value that's given to you is really the slope. Is really the y value. So the first step that we take is we set this y value equal to the function, and we find that x value. But then once you find that x value, then you use that x value to find the derivative or find the slope with the derivative. And whatever slope is given to you, that will lead you to your final answer, because you know that the slope that you found is really just the reciprocal of the slope that the problem is asking for you to find. So it's that very specific process of understanding that relationship between the fact that a function and inverse are always going to have flipped versions of their order pairs, but then at their specific order pairs, their slopes were going to be reciprocals of each other. Okay, so I'll update this on the today's link, and I'll update it with these with this one that has all the notes on it. But yeah, any questions about these topics that are the focus of this final exam? There are certain topics that I just decided to not include on this exam, like optimization. And the reason for that is just, I think optimization is it's a good concept. It's just, for some reason, it just doesn't show up that often on the AP exam. So I want to just focus on the parts that that I feel like have the best chance of you seeing it on the AP exam. Doesn't mean that it's not going to show up. It's just over the years, it's just for some reason just it's not very often that it comes up. Okay, no questions. All right, I'm gonna just start at the beginning and just kind of do a reintroduction of limits and see how much we remember and whether it all is going to come back to you. I had a couple of handouts, but I think I just want to just start from scratch and just have you kind of just follow along here. Okay, so limits. This is what we did at the very beginning of our course. We talked about limits from a graphical perspective. And the first thing that we wanted to establish was that limits and order pairs can be confused with one another. And it's just nice to be able to see the distinction between limits and order pairs at the outset, just to see that sometimes they're confused with each other because a lot of times they give you the same value, but the way that we find limits and find order pairs are it's very subtle, but it's distinctly different. So let's say we are staring at a function, okay, and I ask you for f of 2. F of 2 is equal to what? 3, right? And that highlights the order pair. We could care less what's happening around 2. We're just tunnel vision, just looking at what's happening at 2, and we don't care about anything else. So order pair, we're just looking at the point. But limit is a little bit different. With limit, we're not so concerned about what's happening at that specific point. We're more concerned about how is the graph approaching towards that target? How is the graph behaving as it approaches that target? So the way we evaluate limit graphically is we identify where the target is. The target is 2. And then we pick points on either side, on both sides of that target. So I see that the graph is relatively close, though. So I'm going to pick a point to the left. I'm going to pick a point to the right. And I'm going to draw an arrow towards that target from both sides. And I'm going to ask myself, are those arrows pointing me towards the same y value? And it is, right? They're both pointing me towards y value of 2. Even though it doesn't exist at that point, the approach is consistent. And if the approach is consistent, that's enough for us to say the limit exists. So in other words, using one-side limit notation, from the left side of 2, the left arrow is approaching 2. The arrow from the right is also approaching 2. And even though the point exists somewhere else, these two consistent behavior allows us to conclude that the full limit is equal to 2. Okay, let me show you another scenario. So in this scenario, we have a function. If I ask you for f of 2, you're just going to look for the point, and the point is obviously at 4. But let's see what happens when we try to find the limit. So with the limit process, we do the same thing that we did before. We have to pick 2 points on either side of our target on the graph. And now we're going to move ourselves towards 2, follow the path towards 2 from both sides. And if you draw an arrow, you see that there is a disconnect, right? This arrow is not leading me towards the same path as this arrow. And because there is not a consistent movement from both sides, we can say the limit here doesn't exist. So using the language of one-sided limits, we would say the limit as x approaches 2 from the left side of 2, right? For the left side is approaching 2. From the right side, it's approaching 4. So graphically, we see the arrows don't connect. Using specific limit language, we also see that there's not an agreement on both the one-side limit. So because there's no agreement here, we can conclude the limit doesn't exist. Okay, so order pair and limit, they both involve the point, but from a different perspective, right? So I think this is where students get confused, is because a lot of times those graphs that we're staring at are continuous functions. And if our graph is continuous, then the distinction is going to be very minimal. So let me show you what that looks like. Let's say I had this graph here. F of 2 is equal to 5. The limit as x approaches 2 okay. We pick points on either side of 2. We draw arrows towards 2. And we see that the arrow are both pointing us towards the same y value. So even though we have a completely different method of finding order pair and limits, they look one and the same because it's continuous. So if continuous, your order pair and your limits are equal, or they're not going to be distinguishable from each other. So we see that, if you have a continuous function, you're not going to see the difference in the results, even though the approach is completely separate from each other. So whenever you have any sort of a break in the graph, whether it's a hole or a disconnected graph or a vertical asymptote, that is when you're going to see that distinction between order pair and limits, right? They're not going to be in agreement with each other. Well, unless you have vertical asymptote, then they both don't exist. But if you have a hole in the graph, that is when you're going to see a distinction between order pair and limits. Okay, so just a quick overview as to how to interpret limits if you're looking at a graph. I included this handout under today's link, but I'm just going to pick a few problems from the back page. I want to look at limits from an algebraic perspective, right? We know how to do things from a graphical perspective now, but let's review from an algebraic perspective. So if you don't have this handout, no problem. Just copy this problem down. We'll try number 6 first. So there's two categories of limits without the graph. It's either approaching a real number or it's approaching infinity. So we have a completely different set of steps for a real number versus infinity. Okay. The harder one is the real number, so we'll do the real number first. So with real numbers, the first thing we do is we just plug in that x value. Okay. We don't want to assume anything. All right. Let's plug in that x value, because if we plug in the x value, even though it feels like it's a redundant step, plugging that x value is going to tell you some useful information about what's happening with the graph. Right? I could get a real number, I could get a hole, I could get a vertical asymptote just by, I can just gather that information. It may not lead me to the answer, but it'll give me some visual ideas as to what's happening with the graph. So whenever you see a real number, just go ahead and plug in with limits. Right? And this one has a distractor in the problem, and that is that one-side limit. The one-side limit has an impact. I'll show that to you later, but it's not going to have an impact unless we get a very specific scenario. So the first thing you do is you just focus on the number and don't worry about the one-side limit. It may be a situation where we have to involve decimals, but that's not until down the line, if at all. So let's plug -1 in first. It's always our first step. And what do we get?
0.
Okay, 0 over 0. This is a very useful information. It's not quite the answer, but it gives us some visual idea. We know that there's a hole in the graph. The point doesn't exist, but the limit does exist. Okay, so this is a clear indication that the limit exists. We don't know what that limit is yet, but we're getting some confirmation as to what our next step should be. Okay. So I think some students, they stop here and they say the limit doesn't exist, which is not true. Okay, the point doesn't exist, but that's not what we care about. We care about the limit. Now, if we go back to our expression, we have a very specific scenario for this type problem, right? And that is going through a factoring process. The idea is that there's a hole in the graph. We want to cancel out the hole, right? With all these chapter 1 concepts, where if we know that there's a hole, we're just trying to find a way to cancel that out. Because if we can remove the hole, then we can create a simpler version of the problem that has the hole filled in, and we can find the limit that way. So the numerator is factorable, which is nice. Multiplies to be -6, adds up to be -5. And just like what we suspected, we want those common factors to show up, right? If you get 0 over 0, you know that there's some common factor that you're looking for. Okay, we're going to remove those common factors. And then what do we do next? Okay, yeah, reevaluate, right? Before we're getting 0 over 0, but now we should get something that is a lot more clearer. So -1 minus 6 is -7. That's our limit. Notice the one-side limit has no impact. We don't do anything with decimals because the full limit exists. So it doesn't matter if we're approaching from the left side or from the right side, it's going to be the same. Okay, any questions here? Okay, so now I'm going to introduce something that we didn't do in chapter 1. And we didn't do this in chapter 1 because we haven't learned about derivatives yet. But now that we have derivatives, we can go back and see the fact that we have another option available to us because we're getting 0 over 0. And that other option is called L'Hopital's rule. So I want to show you L'Hopital's rule. In fact, I think a lot of students prefer using L'Hopital's rule because it's just a lot more robust. It can handle a lot more scenarios than, because the factoring method is just for that specific type of problem. But L'Hopital's rule can do a whole wide range of things that a lot of the chapter 1 methods can only do a little of. So here's L'Hopital's rule. L'Hopital's rule says that if I get 0 over 0, I can go through this derivative process of giving me a different look of the expression, which will lead me to the same limit as well. So, but even though this is numerator and denominator, even though we're involving derivatives, this is not the same thing as quotient rule. So with quotient rule, we use it to find the derivative, a slope formula for this expression. But with L'Hopital's rule, we use the derivative to get to the limit, which is a different process. Okay, thank you. Good day. Good day. So this is what it looks like. So we're going to revert back to the original problem, and we're going to approach it from a different perspective. We're going to do L'Hopital's rule. So L'Hopital's rule says, we got 0 over 0, so we know we can do it. We take the derivative of just the numerator. What's the numerator's derivative? Power rule, right? So 2x minus 5, okay? Okay, so no quotient rule here. We don't have to go through that whole quotient rule. We're just doing something for the specific, we're just involving derivatives to find limits. So we're not really dealing with this function here. Okay, what's x plus 1's derivative? 1. So it looks a little different than our factored form, but this will get us the same results. Before this gave us 0 over 0, but now we have a different version of the problem, which will also give us the same limit. So let's plug -1 in to confirm. 2 times -1 minus 5. -2 minus 5 is -7. So now it kind of opens up a whole new set of things that you can do with limit problems. And I think L'Hopital's rule really comes in handy for problems that, let's say something gives you 0 over 0, but it ends up not being factorable, right? If something's not factorable, this method is not available, but we always have L'Hopital's rule in our back pocket to use. So ultimately, it just gives you more options if you see a limit problem. Maybe you decide that you want to go through this method for certain types. Other types you want to go through L'Hopital's rule. I think the more options you have, the easier problems can be, because you can choose one option versus the other if you run into a dead end with one. Okay, I didn't get a chance to put this type of problem on this sheet, but maybe you can just cross out one of the problems below or put this problem here. And I want to show you a different scenario. Limit as x approaches 0. Okay, we're not going to assume anything, right? What's our first step? Yeah, plug in 0, right? We need to know what's happening first before we can jump into all these other methods. Because if we get a real number out of this, then there's nothing more that needs to be done. Okay, so plug in 0, we get √2 plus 0 minus √2. I get 0 over 0. Okay, so this is confirmed. There's a hole, limit exists. We have to look for it. Now in chapter 1, we had a very specific form, a specific way of handling these radical problems, and that is using what we call the conjugate method. So the conjugate method is trying to find a matching term with the denominator. Now, if you look, this is what's causing. We want an x to show up in the numerator so we can cancel the x's out. We know already our culprit, it's that x. But right now, the x is not very clear where it is in the numerator. So the conjugate method allows us to get this radical cleaned up in a way that we can clearly see a whole that we can cancel out. Okay. So the conjugate method is multiplying the numerator denominator by exactly what you see in the numerator, but with one slight change. We're going to change that sign that sits between the two terms. Okay, we're going to FOIL, we're going to clean up the numerator, but the denominator you're going to leave alone. And the reason why you leave the denominator alone is because this x is ready for you to cancel out, right? We don't want to lose that x by distributing it through. It's just the numerator that we want to try to clean up. Now, the nice thing about multiplying conjugates is that a lot of things are going to clean up nicely. The only thing you have to worry about is multiplying the first pair together and then multiplying the second pair. So square root times square root, I'm just left with the term inside. Negative root 2 times root 2 is just going to be 2. And then leave the denominator as is. Don't do anything with it. Okay. You find some like terms there, right? 2 minus 2 is 0, so that goes away nicely. And now we see the cause of our issue, right? The x and x are now clearly there for us to remove. So we know that the whole has now been removed. Careful though, when everything disappears from the numerator, there's still a 1 left over, right? And now we can evaluate the limit or reevaluate the limit and see if this gives us a real number that we're searching for. Okay, so before we got 0 over 0, but now that the whole has been removed, when we reevaluate, we should be able to get down to a real number. So plug 0 in for x. Root 2 plus root 2 is going to be 2 root 2. That's a real number. No need to rationalize. Right, a very specific method for a very specific scenario, right? So I want us to revisit this problem again. What else could we do because we're getting that 0 over 0? Yeah, we can also do L'Hopital's, right? We didn't do this in chapter 1, but let's revisit this problem and see that we can do this using L'Hopital's rule. Okay. All right, so I'm going to go back to our problem here. Right. We know that 0 over 0 is there. We know that L'Hopital's rule is an option. So if you wanted to bypass this conjugate method, you can always bypass it if you want to do L'Hopital's rule. But we do need to do a little bit of setup here. This square root is really not, visually is not as helpful. So let's rewrite that as rational exponent. Okay. we're going to apply L'Hopital. So I'm going to take the derivative of the numerator, and then separately, I'll take the derivative of the denominator. So this is chain rule, right? Outside derivative times inside derivative. So we do outside first, bring down the 1/2, keep the parentheses, subtract 1 from the exponent. Outside derivative is taken care of. Now we move to inside derivative. So the derivative of 2 plus x is just 1. Okay, what happens to the root 2? It goes away, right? 0, it's a constant. Okay, so we took the numerator's derivative, that's good. And now we focus our attention on the denominator. What's x's derivative? 1. So now we have a different look of the limit problem. And the hope is that when we reevaluate, we can work our way down to a numeric answer. So I'm going to plug 0 into the x and see what that gives me. Okay, 2 to the negative 1/2. I can resolve that negative exponent by pushing that 2 to the denominator. So it's going to end up sharing the same space as this 2 down here. And we can think of 2 to the 1/2 as square root of 2, right? So same answer, different process. But now that you know L'Hopital's rule, it can basically handle all the other limit problems that we saw in chapter 1. As long as you take the derivative correctly, right? Understand the process there. So in light of this, let's do one that we may not have seen before and see if we have a path to the answer here. What if I gave you sine of 3x over sine of 4x? Right. I didn't go through trig properties with you or trig derivative rules or trig limit problems with you before, but let's just use the process that we've been doing and see if we're able to reach the answer. So what would you do first here? Yeah. If you see a real number, you're going to just plug it in, right? So if I plug 0 in for x, I get sine of 0. 3 times 0 is 0 over sine of 4 times 0, which is 0. Using unit circle or using your calculator, you know that sine of 0 is just 0. So we have 0 over 0, which means that we could use what? Right. We don't have factoring methods. We don't have conjugate method, but we do have L'Hopital's available to us to use. So let's explore the derivatives for the numerator and denominator separately. So sine of u, the derivative for sine of u is cosine of u times u prime, right? The derivative for sine of 4x, same process, cosine of 4x times 4. So now that we have a derivative, what can we do here? Let's reevaluate, right? Before we got 0 over 0, and after this process, hopefully we can get down to a real number. Okay, using your calculator or unit circle, you know that cosine of 0 is 1. So you see how robust L'Hopital's rule can do pretty much anything you want it to do As long as you get 0 over 0, and as long as you have derivative methods available, and you're taking the derivative correctly. But then I want to make sure that we don't confuse this with quotient rule, right? Quotient rule, we can't just take the derivative numerator and derivative denominator and be done. This is a very special process, not to find the derivative, but to use the derivative to help us find the limit. Okay, questions here? Okay, I want to just see if I can squeeze in a few more things here with limits. This goes back to real numbers, but let's see what happens here. Let's see what happens here where our result is a little bit different. So limit as x approaches -2 from the left side of -2, 3 minus x over 4 minus x squared. Right, first things first, right? What do we do first? Yeah, -2, right? No decimals, okay? We don't do decimals until we get a certain scenario. So -2, let's see what happens. We want to gather information. We want to know what category we're dealing with here. Okay, and what do we get?
Sorry.
Yep, you're right.
Or sorry, yeah,
5 over 0, right? 5 over 0. Now, this is not 0 over 0. So this is not a whole situation. This is something very specific. What do we know about what's happening here based off of this result? Okay, more specifically though, what's happening visually? Not a whole. The whole would be 0 over 0. Yep, good. Vertical asymptote, right? So if you see 5 over 0, it's a vertical asymptote. Which visually is very helpful, right? We know that if we're dealing with a vertical asymptote, we know the limit doesn't exist. Which would be our answer, except for the fact that now we look and we see that it's not asking for the full limit. It's only asking for the limit from the left side of -2. So graphically, maybe the asymptote is forcing the graph to go up, or maybe it's going down. And we now know that the limit doesn't exist, but we're choosing between two options. It's approaching an asymptote, and that graph is either rising up to infinity or it's going down to -infinity. So because we're down to two options, we're going to test a decimal to help us narrow down between those two options. So this is when we involve decimals. We only involve decimals when we get to this very specific scenario where the limit doesn't exist, and we go back to the problem and realize that it's asking just for the behavior towards that asymptote. So I'm going to test a value to the left of -2, but I want to test a number that is close to it, so -2.1. So I'll plug -2.1 in for x. And I just want to, I don't care about the number. I just want to know what the sign is. So numerator, I get positive. Denominator, I get negative. So positive over negative is negative, right? So I know that my graph is going to look more like that. So I know that my one-sided limit is -infinity. Okay. One final thing to go over is the fact that we talked about limit as x approaches a real number, right? We went through most of our time was spent doing that. But then there's also scenario of limit approaching infinity and negativity. We have a different set of steps for that. And I just want to show you real quick. It's a lot easier. It's a lot faster. If you see infinity, we don't plug in numbers. We go directly into locating the highest exponents between numerator and denominator. So in this case, if I see infinity, I'm going to go searching for the highest exponent. So I see 5 up here. I see 5 below. They're both the same. If my degrees are the same, then my limit is just taking the coefficients attached to those variables and taking the ratio. All right. So limits through infinity or negative infinity is really quick, potentially, if we know what we're doing. So no need to factor. L'Hopital's rule can actually be applied here, but it doesn't speed up the process. It's a lot faster to go through this method of just looking for comparing exponents. Right. Now let's say we do infinity or negative infinity, but then we're comparing degrees and we realize the degree in the denominator is higher. If the denominator has a higher degree, then the denominator is rising it's increasing at a faster rate, which means that your fraction is getting smaller and smaller and smaller, and so your limit is 0. And then the final scenario is where you're approaching infinity, but your numerator ends up being a higher exponent, a higher degree than the denominator, which means that your numerator is rising at a faster rate than the denominator, which means that it's either going up to positive infinity or it's going down to negative infinity, depending on the sign. So if you're down to this scenario, then to choose between those two options, you look to see where the graph is headed. It's headed towards infinity. I'm going to test a number that is relatively large, like 100, and I'm just going to plug 100 in for x. So if I plug 100 in for x, I get 200 minus a much larger negative number, so I get negative. Denominator, I get positive. So negative over positive is negative, so therefore negative infinity. So in this situations where the numerator has a higher exponent than the denominator, it requires a little bit more work. These scenarios are the ones that are really quick. You can just find the answer just by within a second. But this scenario requires a little bit more. But at least, through this class period, we're able to kind of review all of chapter 1 and also see how L'Hopital's rule can handle a bunch of situations that we couldn't do when we started chapter 1. All right, thanks everyone. Hope you guys have a great day. Fill out the survey if you haven't. Otherwise, I'll see you tomorrow.